All right, guys, so in this video, we're going to look at Chapter 7. We're going to revisit some of the periodic properties of the elements that we talked about in Year 1, and then we're going to kind of look at those in greater depth. We're also going to look at group trends in the second part of this video. So hopefully, this first part will be mostly review. We know that, from last year, Dmitry Mendeleev is responsible or is given credit for the development of the modern periodic table. This is a pretty interesting graphic here. It shows you the elements that were known at certain times. So I think Mendeleev was working sometime in the late 1800s, maybe early 1900s, somewhere around. Let's see if we can get this pen to work. Yeah, somewhere around in here. And so when Dmitry was looking at stuff, he said, well, let's organize these by, atomic mass. That was the main identifying property of elements at the time, and so that's what he used. Now, the reason that Mendeleev gets that credit is because when he set up his periodic table, he left these blanks in it. And so one of the most famous ones is what he called Eka aluminum and Eka silicon and some things like that. So underneath silicon is germanium. And when he was setting up his table, right, so here's silicon, and next to it you have phosphorus. And underneath of it, there was arsenic, and arsenic, I believe, was known at the time. And when he was organizing his tiles, right, this should be, there we go, aluminum. Instead of just putting things there that they knew about, he left them blank. And he said, yeah, I don't think we've discovered these elements yet. And so he used the term Eka silicon. So like this would be Eka silicon, and this was Eka aluminum. And he made some predictions about it. So he said, like, hey, the atomic weight for Eka silicon is going to be 72. When it was discovered, it turned out to be 72.6, right? So the density would be 5.5, the density turned out to be 5.35. He was pretty, accurate, and he made these predictions using his knowledge of the trends. Now, like we said, he used the atomic mass in order to organize the periodic table. But if you look at some things like tellurium and iodine, I believe, my periodic table here, yeah, tellurium is number 52. It's 127. So tellurium is number 52. It is 127.6 on the periodic table. Iodine is number 53. It is 126.9. So we can see here an example where it's not, organized by increasing atomic mass. That was brought about by a guy named Henry Moseley, who unfortunately lived a very short life. He died in his 20s in World War I. Like 1915, I think he died, which is a shame because, he is the person who said, hey, we should organize the periodic table by the increasing atomic number. So he was pretty bright, probably would have contributed some more science. But anyway, after Ernest Rutherford discovered the nuclear atom, so that the atom had a nucleus, Moseley said, we should organize our periodic table by increasing atomic number. This led to some more support for the idea of periodicity, which is the repetition of certain properties after set blocks. So you go so far, you go 8 blocks or you go 9 blocks, whatever it is, and this pattern repeats. And in our chapter, and for our purposes, we're going to look at the size of the atoms. We're going to look at ionization energy and electron affinity. These are things that we looked at last year, but we're just going to look at them a little bit deeper. The fundamental property behind these trends, though, that I really tried to hammer last year is effective nuclear charge, right? Remember ENC. So effective nuclear charge is a description of the attraction between the nucleus, which is positive, and the valence electrons, which are negative. Electrons are attracted to the nucleus, but they're repelled by the other electrons that are in the electron clouds because negative charges repel negative charges. So the forces that the valence electrons are going to experience have to be a sum of the repulsion and the attraction forces. Now we can calculate effective nuclear charge with this little formula right here. if Z effect, so the effective nuclear charge, so the effective number of protons, right? Because remember, Z is the atomic number or number of protons, is Z minus S. S is what we call the screening constant, and usually for us, we can just use that as the number of inner electrons. Now, that is not entirely accurate. If you go on to do some more advanced chemistry, I didn't see what S actually was until I got to grad school in my master's in chem. But if you go on and do some more advanced chemistry, you'll see how to calculate S. For our purposes, just use the number of inner electrons unless they give you an S value. Now, effective nuclear charge, or ENC, is a periodic property, so we can describe it in terms of trend arrows. It's going to increase across a period. It's going to decrease down a group. If you graph it out, and this is a pretty cool graph. I like this graph. Let me move this thing out of the way. Sorry, I lost my train of thought. This is a pretty cool graph. I like this graph. Sorry. If you look at this black line right here, this is just the charge of the nucleus. So that is just how many protons there are, right? This is, you could also say, instead of charge of the nucleus, you could just say atomic number. So as we go to the right, obviously the atomic number is increasing by 1 each time we go to the right, right? Lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, so on and so forth. If you look at just the 1s electrons, which have no shielding, right? So you have the nucleus. Let's say the nucleus, right? We know nucleus could have any number of parts, right? So there's our nucleus. If you are a 1s electron, you never have any shielding, right? There's no inner electrons between 1s and the nucleus. So if you were to calculate the core 1s electron's effective nuclear charge, well, it's just going to mirror the protons. Now, you notice it's a little bit lower, and you can see it's kind of starting to tail off, right? That's probably because, I know it's because the size of the atom is getting bigger, right? It's changing there. Now, if we use equation 7.1, which is the ZEFF equals Z minus S, and we assume S is just the number of inner electrons, core electrons, we get this blue graph. And we can see that, as you go to the right, effective nuclear charge is rising. And then, because it's a periodic property, this region right here is when we go from the noble gas furthest on the right, neon, right, number 10, over to 11, which shifts us back to the very left-hand side of the periodic table. Again, it starts to climb. There's argon. We would expect, right, the next little green triangle to be down here somewhere. If you look at advanced methods, which are the ones I was talking about for, where you have a constant for S, you can see that S is pretty close, all right? Sorry, not S. The graph is pretty close when we know what S really is. And then there's this thing right here called Slater's rules. Slater's rules is also a concept that I didn't encounter until grad school, which allows us to calculate the actual energy of the electrons and how they're going to impact the shielding of the valence electrons. So you can see that with Slater's rule, we have, kind of a happy agreement between, especially if you look like right here, that blue and that green line. So because the green line is close enough, that's what we're going to go off of. It's going to illustrate our trend well enough. So this is the equation you will use to calculate effective nuclear charge. Now, the next trend we're going to look at is the size of the atom, or I guess the first trend. We're going to say ENC is a fundamental trend. This is going to be the first trend that depends on that. So the non-bonding atomic radius, which is often called the van der Waals radius, is half of the shortest distance separating two nuclei during a collision of atoms. Now, last year, we said if you want to know, how far two atoms are apart, if you want to find their atomic radii, you find, two hydrogen atoms, right? Because hydrogen we know is a dimer, and we take the distance between their two middles and we half it, right? 1/2 d. And that's great. And nobody asked any questions because they're like, oh, yeah, that makes sense. If you don't form dimers, right? Like, let's say I want to figure out how big neon is. Well, neon isn't going to form a dimer with neon. So in order to figure out, these non-bonding electrons, or not, sorry, non-bonding atoms, we just collide the two and then we measure it, right? So once you get close enough for a collision, you're going to have electron-electron repulsion. That's going to arrest the movement. That's as close as they can get. And so we cut that in half and we say that is the size of the atom. That's the non-bonding atomic radius. Okay. When we look at the size of the atoms, we notice that the atoms get bigger as you go down a group. You notice that atoms get bigger as you go to the left on the periodic table, or on a periodic row, rather. So we would say that on the periodic table as a whole, let's see if we can sketch one of those out. Atomic radius increases down and to the left, with francium being the largest atom. Now, something that we can use to explain this is the effective nuclear charge. So why, if I go this way, why is the radius smaller? Well, as you go to the right, we know that the effective nuclear charge is going up, right? It goes up with the number of protons, more effective nuclear charge. More effective nuclear charge means the electrons are pulled in tighter, which means the radius is getting smaller. Right? If we want to know why it's increasing from the bottom of the group, well, this would actually be explained by shielding, right? So there's more shielding here, right, than here. So I don't have as many electrons in the way for helium's electrons, so they take the full E and C. So as N gets larger, that is the number, right? 1, 2, 3, 4, 5, going down the groups, the first principal quantum number. As it gets bigger, as N gets larger, I have more subshells, right? More subshells of electrons. And when we look at the sizes of ions or ionic radii, it's again determined by interatomic distances between those compounds. So it's going to depend on the nuclear charge. It's going to depend on the number of electrons. It's going to depend on which orbital the electrons are in. That's actually important. And something that we can take away from this is that cations are going to be smaller than their parent atoms. And last year we just said, yeah, they're losing electrons. So yeah, I mean, that makes sense, right? They can get further apart. Now we want to be able to explain why. So this is the why. Repulsions between the electrons are now reduced. There are less electrons there, which means less overall negativity, right? Less number of negative charges. And so the repulsion between electrons is lessened. That allows them to get larger. With anions, we have, they're getting bigger than their parent atoms. And because of that, they, if we want to explain it, we have electrons added. So the repulsions are increased. When, repulsions are increased, the electrons want to get further away, all right? And that increases the size of the atom. Right here was our former. Now we have another electron in there, so now they got to get further away, all right? Now, something new is called an isoelectronic series, and we can compare trends among isoelectronic atoms because they have the same number of electrons. So what we'll notice is that ionic size is going to decrease with an increasing nuclear charge. Again, that makes sense, right? More effective nuclear charge equals smaller sized atoms. So it stands to reason that the same thing would be true in ions. So here is an isoelectric series. All of these have 10 electrons exactly. All right. And so if they have the same number of electrons, we call them isoelectronic. Now look at the ionic radii, right? It's measured in angstroms. That's the angstrom symbol. And you'll notice that as the nuclear charge gets bigger, okay, our radius gets smaller. So like oxygen, it has 8 protons. Let's just see if it lines up with protons. Fluorine has 9 protons. Sodium has 11 protons. All right. Magnesium has 12 protons. and aluminum has 13 protons. There we go. And so looking at the atomic number, right, it's increasing, making our ions smaller. The next term we're going to look at is ionization energy, which we usually just abbreviate as I or I sub 1 for the first ionization energy. This is the minimum amount of energy required to move an electron from the ground state when an atom is a gas. That is important. Like this is important here. It's called the first ionization energy because that's the first electron. The second ionization energy is talking about the second electron. There's any electron you want to move, you have to have, a third, a fourth, a fifth ionization energy, whatever it is. The higher the ionization energy, right, the more difficult it is to remove electrons. Why is that? Well, it takes more and more energy to remove each successive electron because once you start removing electrons, the effective nuclear charge, right, that's being applied to each electron is technically increasing, right? I'm not changing the number of protons, but I am reducing the number of electrons. So if you kind of think about effective nuclear charge like, butter on toast, I have my effective nuclear charge is the butter. I have the same amount of butter, right? We're going to say, one little slice every time. So we'll just draw that out. Here's our butter. We have this much. There's a little cube of butter. Well, if my toast is that big, all right, I can get the butter, spread out. On the other hand, same amount of butter, right? Draw that again. It's roughly the same amount. If I start removing toast, right, we've cut it in half. Now, same amount of butter, I can spread that much, much thicker. So as I remove electrons, that effective nuclear charge is kind of smeared across the remaining electrons in a greater quantity. So if we look at like our first ionization energy, right, I1, you'll notice that for sodium, to get rid of the first ionization energy, not a big deal. 496 kilojoules per mole. That's the unit here. To take the second electron from sodium, 4,562 kilojoules per mole. You're talking about like a factor of 10 increase. That's ridiculous. And when you think about it, it makes sense, right? I have sodium, which is 1s2, 2s2, 2p6, 3s1. When I take that first electron, I become 1s2, 2s2, 2p6. And I have full valence. I'm stable. Now, if you're going to take that second one, you're going to go from 6 down to 5. Yeah, you're going to get fought. The electron does not want, or the atom does not want to give that electron up. If I look at, say, aluminum, right? First one, easy to take. Second one, 3 times as hard, right? Third ionization energy, I go from 600 to like 2,800. That's a factor of over 4 increase. But then look at the jump to get the fourth one. We know aluminum can be +3. That's fine, right? That's the charge it likes to be. It makes it stable. But to make an aluminum atom a +4, not going to happen, okay? So the more electrons you remove, the greater the amount of energy each successive one takes. And you'll notice that once you start to try to take inner electrons, it's rough, okay? Very difficult. Now, as far as the trend itself, the first ionization energy increases across a period. Generally, it's going to decrease down a group. The S and P block have much larger value changes between their first ionization energy. The D block's pretty slow. It's pretty gradual. F block's very, very small variations, if any at all. Sometimes they'll be the same. Now, there are a lot of different things that influence ionization energy. The smaller atoms have higher ionization energy values because of the greater effective nuclear charge, right? There's less shielding going on, so there's, greater control by the nucleus there, that positive charge. You can see that helium definitely has the highest ionization energy. Remember, helium is 1s2. It's super stable. It's happy. It does not want to give up that electron. There are some irregularities in this. Okay, if you look at the orbital diagram, okay, then this is gonna lead to some it's gonna lead to some problems. So if you're trying to understand the irregularities, and I wish let me go back here. Let me see if I can see one here. So this was the irregularity that we're talking about. So nitrogen, if I'm looking at the orbital diagrams here, right? Let's do nitrogens here. So I have 1s2, 2s2, 2p3. So that's 1s2, 2s2, 2p3. Okay, these electrons right here are in different orbitals. So they're not really repelling each other. But if I look at oxygen, 1s2, 2s2, 2p4, up, down, right? 2s, up, down, 2p. All right, so we go up, 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 down. All right, that electron right there, it really wants to be taken away because these two electrons, they are repelling each other. And so because they're repelling each other, the ionization energy of oxygen is slightly lower than the ionization energy of nitrogen. And we can see that in all of these, that's true, right? Till you get all the way down here. So that would be an example of these little irregularities in the general trend. So this electron is unhappy. It wants to be taken away, okay? This is a much more stable conformation than that because there is less repulsion among the electrons. Now, when we look at the electron configuration of ions, okay, we're pretty much always going to take electrons. Well, actually, we're always going to take electrons from the highest N value, the highest principal quantum number for our cations. So lithium is 1s2. It's going to lose a 2s electron. Iron is 2 plus. It's going to lose that 4s electron, right? Because normally iron is 3p6, 4s2, 3d6. Well, 4 is the highest energy level. So those are the first electrons that are going to be lost. Electron configurations for anions, you're trying to get that nice stable 8. So it's going to fill S2P6. So for fluorine, right, fluorine is normally 1s2, 2s2, 2p5. Well, when you gain an electron, it's going to go right there into the 2p5 in order to give you that 2p6, that NP6. Last one we're going to look at is electron affinity in this video. That is the energy change accompanying the addition of an electron to a gaseous atom. This usually gives off energy when you put an electron in there. You have an exothermic reaction. Exothermic reactions are negative. We'll learn more about the signs for exothermic and endothermic when we do thermodynamics. But because we're kind of thinking about it like this, right? Chlorine is the system that I'm studying. When I add that electron, energy leaves the system. So we say that for the system itself, the amount of energy there is less than before. So we'd say that's an exothermic reaction. It's given off the energy. And since we lost energy in the system, not in the surroundings, but in the system, we give it a negative sign. So it's an exothermic reaction. So that's going to be a negative value. So when we look at these values here, we're seeing that, for the most part, those are negative values. There's not a lot of change in the group. We can see that, in this group, these are pretty similar, very similar in the alkali earth metals, extremely similar in the noble gases. But across a period, it's usually going to increase. Now, that's not always true, and it's for the same reason that we have that little hiccup in the last trend that we looked at. So in group 2A, all right, I have a full sublevel. So it's not going to trend up. This actually is a, an anomaly there. The group 5A P sublevel is half full. So that's the one we just looked at, right? Nitrogen is, what's that, 2S? Yeah, 2p, sorry, 3. So I have that nice half full thing going on there. So if I want to add an electron, I want to make it more like oxygen. If I'm adding an electron, I'm adding repulsion, and that's going to take extra energy there. So that's not good. If you look at the noble gases, we have a full p sublevel, right? So all these guys are in NS2, NP6, right? So we're full. That means if you want to add an electron to that, you're going to create, the next S, right? N+1 S1. And that's going to make them unstable, right? They're no longer going to have 8 valence electrons, or in helium's case, 2. And so you have a positive number for electron affinity, which means it's endothermic, which means you have to put energy into the system in order to make it happen. And so that's an unstable activity. That's not going to be an easy thing to do. Now, when we look at our metals, nonmetals, and metalloids, just to kind of wrap this video up, we know that we have increasing metallic character down and to the left. So, what happened there? Francium is the most metallic element. We know that our metals and our nonmetals are different, right? We know our metals are on the left. They have a tendency to form cations. Our nonmetals are on the right. They have a tendency to form anions. Hopefully you remember that from last year. Make sure that you brush up on the properties of metals, right? And something that's important to know, most of the elements in nature are metals, okay? If you were to reach your hand into a random bag of elements from the universe, you're most likely going to pull an element out of that bag that is a metal. Remember that metals are shiny, right? They have luster. As one of my kids said earlier this year, they're lusty. That's not the word that we use for that, right? It's luster. They're good conductors of heat and electricity. They're malleable, which means they can be hammered into sheets. They're ductile, which means they can be pulled into wire. With the exception of mercury, they're all going to be solids at room temperature. And they're going to have low ionization energies because they want to give those electrons away. They want to form cations, so that it's easy for them to do that. Our metal chemistry, as far as metals and nonmetals, those are going to be ionic compounds, right? We can look at the Pauling scale to determine that. Remember, a metal oxide is so like a metal and water, a metal and oxygen are going to tend to be basic when you put them in water. When we talk about nonmetals, remember they're on the right side of the periodic table, on the right side of the step break. Some properties that we should be aware of, they are solids, liquids, or gases at room temperature, right? That can be any of the three. It just depends on the element. They're going to be dull, right? So no luster. They're really brittle. So you can see in this picture, sulfur has been broken with this little hammer. No big deal. They're poor conductors of heat and electricity. They're usually going to have really big negative electronegative values. They're going to form anions pretty easily. So they want to be negative ions. When you have a nonmetal oxide, those are going to become acidic. And if you have just nonmetals, they're not ionic, right? They're molecular compounds, which we'll talk more about in the future. So make sure you know kind of the differences here between our metals and our nonmetals. Obviously, in the middle of those, we have the metalloids, which are going to share characteristics of metals and nonmetals. All right, in the next video, we're going to look at some group trends, but that's it for this one. So let me know if you have questions. I'll be glad to give you a hand.